Welcome again to Mathematics Solutions, MMS. Today, I want to look at an introduction to abstract algebra. And in abstract algebra, I want to look at what a binary operation is. Now, before we understand what a binary operation is, we need to understand what is an operation. An operation is a rule that defines what is to be done, defines what is to be done one or more elements of a given set. One or more element the given set. The given set. Now, there are two types of operations. We have binary operation, and also we have the unary operation. So there are two types of operations. They are two types of operations. Namely, binary and unary operations. Binary and unary operation. Unary operations. Now, examples of unary operations is where an operation acts on only one element. So for unary operation, an operation that acts on only one element. On only one element. For example, e.g., the square root, negation, the squares, etc. But for the binary operation, these operations that acts, these are operations that acts on two elements. Two elements. Maybe for example, we have the union, we have the intersection, we have the addition, we have the multiplication, we have the subtraction, etc. Now, what are the properties of binary operation? Let us look at the properties of binary operation. So the properties of binary operation are, properties of binary operations. Number one, you have the Crochet property. Crochet property. You have the Crochet property. Now, in Crochet property, we say that suppose S is a non-empty set Suppose S is an empty set that is S is not equal to empty set, then S is said to be closed. Said to be closed. Under multiplication and under operation star and an operation star, if and only if and only if A star B is in S, if and only if A star B is in F for all A and B in S. For all A and B in S. Then we shall say that it satisfies the Cauchy property. If at all, maybe you carry out an operation between two elements, and it happens that the result of these two elements also belongs to the same set S. And so therefore you can conclude and say that this set satisfies the Cauchy property. Now, for examples, we can have maybe examples you can have will be the set of integers is closed under addition. So that means that if I pick maybe any two values from a set of integers, for example, if I pick maybe 3 and -5 from a set of integers, then 3 plus 5 plus -5 is equals to -2. And we know that -2 is also a member of the binary operation. So that is how you check whether a set satisfies the Cauchy property or not. The other property we have is commutativity property. We have the commutative property. Number 2, commutativity property. Again, here we say that if we let S to be an empty set, so let S to be an empty set, and star be a binary operation, S, then we say that then let's wrap that. Then we say that star is commutative on star is commutative on S if and only if for all A and B in S, A star B is equals to B star A. Example, can have an example. example, determine whether a set of integers satisfies commutativity axiom. So solution say that right that A, or else maybe you can say you can now pick the values from the set of integers that 10 and 4 chosen from set of integers, then 10 maybe times 4 is equals to 4 times 10. And now in this one, now you get that on the left-hand side, it is 40, which is equals to the right-hand side, which is 40. And this 40 also belongs to set of Z. Now, in this case here, we have determined whether the set of integers under multiplication satisfies commutativity property. So the other property of a binary operation can check is associativity. Number 3, we have associativity. So what do we mean by associativity? Again, we say we let S be an empty set. Let S be a non-empty set. That is S is not equal to empty, contains some element. And star be a binary operation. Be a binary operation on S. Then we may say that star is associative on S if and only if now if and only if what? If you have now for all A, B, C from S, we have A star B star C being equal to A star B star C now. If this one here, in this case now, we say that the set satisfies associativity if this condition is satisfied, like that. Like what we mean, if you carry out the operation using maybe now examples The examples of these sets are, for instance, we have example can have maybe the set of real numbers, rational numbers. You also have the complex numbers and natural numbers. They satisfy associativity under addition and multiplication. So the other property of a binary operation we'd like to check is existence of identity element. The existence of an identity element. So let us check. So number 4, existence of an identity element. Now, in this, we may say that um, let S be an empty set. Let S be an empty set, and the star be a binary operation. Be a binary operation on S. Then star admits an identity. Star admits an identity element in S if and only if for all A's, for all A in S, there exists an element E also in S such that A star E is equals to E star A is equals to A. So we say that E is the identity. Say that E is the identity. So that E is the identity element in S. Say that E is an identity element in S. So let us also look at the property number 5, the existence of inverse. So when do we say that a set contains an inverse, or maybe an element contains an inverse? So what is an inverse of an element? Definitely, when you speak about the inverse, then there must be, if an operation is taken to over that element, then we should get an identity element. Then by then, we should say that that element is an inverse of the other element. Now, what do we mean by that? We mean that number 5, let us have number 5 here. Existence of an inverse. Existence of an inverse. And in this, we say that we let S be an empty set. Let S be an empty set, and star be a binary operation, be a binary operation on S. Then we say now, like we're saying that if S is an empty element and an empty set, that implies that S contains some element, and we have a star which is a binary operation on S, then we say that there should be existing. Then there is an E in S, which implies that admits star. Like, what do you mean in this existence of an inverse? I think that if S is a non-empty set and the star is a binary operation on S, and so we also have an identity that is in S, then you can only say that there exists an inverse, and then let us erase this one. And just simply say then star admits inverse in S if and only if and only if for all A in S there must exist an A inverse in S such that A star A inverse is equals to E, and also A inverse star A is equals to E. Now, so let us look at what we call the Caylay table. Table. Now for the Caylay table, we say that let S be an empty set and star a binary operation on S, and S is finite, and S is finite. Then we can construct a table. We can construct a table for the system S star. Now, procedure. Construction of construction of the table. So what you do, we list all the elements of S, list all the elements S, then and across in the same order. Across the same order. Then then AJ and AI, or maybe AI by AJ entry is the element of the intersection. The element of the intersection of the ith row and jth column. Jth column. So that is if S is given by S is equals to A1, A2, A3, all the way to AN. Then the Caylay table for S, then the Caylay table for S is given as now. Here we mean that we want to develop the Caylay table of S, and the operation here is star. So what you do, you draw a table of this kind. So we put the operation here, and then I have A1, A2, A3, all the way up to AN. Then you also have A1, A2, A3, up to AN. So in that case, the element here to be A1 star A1, then A1 star A2, all the way up to A1 star AN. Then the same case now in this to be A2 star A1, A2 star A2, all the way up to A2 star AN. And this will continue like that. Continue like that. Now, example. You can have an example here. Example, suppose S is given by, suppose S is equals to 1, -1, I, -I, where I is an imaginary, it's an imaginary number equal to the square root of -1. Then under multiplication, develop the Caylay table under multiplication. Under multiplication. Solution. So we want to develop the Caylay table for S and star. And with that, we're going to draw. We've said we start by drawing the table and we put the operation time multiplication here. Then now we have 1, -1, I, and -I. The same way, we have 1, -1, I, -I. So this is going to become 1, this will become -1, this will become I, this will become -I. Therefore, this one to become -1, this one to become 1, this one to become I, -I, that is, then this one to become I. Then this one to become what? Because it is negative I times 1 to become I times -1 to become I times I to become I squared, which is equal to -1. Remember, I squared is equal to -1. And then we shall have I and I become +1 because now we have -I squared, which is equal to 1. Same case now when it comes to -I, this will become -I, this will become I, this one to become +1, and this one to become -1. So I believe maybe it's not difficult to develop a Caylay table for that. Let us define a group. Let us look at what is a group. So we can check what. In the next class, we shall be looking at groups. At the groups. Thank you so much. Thank you for watching Mathematics Solutions, MMS, the Mathematics Haven.